Okay, so first of all, today what we're going to talk about is something called spontaneous reactions. Does everyone know what spontaneous means? Happens all on its own. Okay, so we're going to talk about spontaneous reactions. So spontaneous reactions are naturally occurring reactions. It happens on its own. They favor the formation of the product. So this would be like if I put a piece of ice on the table over there. It's obviously warmer than freezing in this room right now, correct? So is it going to melt? That's a spontaneous reaction. It is going to favor the product side. The product side is going from ice to liquid. Okay, that's going. If it was below freezing in here, would that happen? No. So that would be a non-spontaneous reaction. So when we're trying to determine if something's spontaneous, we have to take into account enthalpy and something called disorder, which we'll get to in just a second. Okay, so we have to take into account a lot of things when we're trying to determine how spontaneous something is. Well, we also have something called non-spontaneous reactions, and these are the exact opposite. They do not favor the product formation, nor do they yield products. If they're non-spontaneous, they're probably not going to happen, so therefore you're not going to get your products. Okay. When we're talking about spontaneity, we are not talking about the rate. Okay, we're not talking about how fast the reaction happens or how slow the reaction happens. When we're talking about spontaneity, it has nothing to do with those factors. Okay, reactions can have both spontaneity and rate of reaction. And honestly, the two things that affect how spontaneous reaction is your temperature and your pressure. Just like the example I just did with the ice, all we have to do to change the spontaneity of that reaction is change the temperature, right? Okay. If we're talking about water vapor in the gas form, if we change the pressure, it's going to cause it to solidify into liquid, right? So on and so forth. So if we change temperature and pressure, it also can change how spontaneous a reaction can be. Okay, so we've spent a few days talking about enthalpy. What's the symbol for enthalpy? Delta H. When I'm talking about enthalpy, what am I talking about? Kaylee was asking me about it yesterday. Heat. When I'm talking about enthalpy, I'm honestly talking about how much heat is being absorbed or released into the system, correct? More complicated than that, but on the basic scale, it's what we're talking about. All right, so the next thing that we're going to talk about, we just talked about enthalpy, so now we're going to talk about something called free energy, and it has the symbol of delta G. Okay, does anybody remember talking about energy back in physical science back in the day? Energy and something else go hand in hand. Does anyone remember? You can't have energy. You can't produce energy unless you do work. Does everybody kind of remember that? So free energy is the energy available to do work. Okay, no reaction, though, is 100% efficient. Just like when we talked about machines, no machine is 100% efficient. You always have energy loss due to heat of reactions, due to heat, due to friction, there is an enormous list of ways that heat can be lost. So therefore, just like machines are not 100% efficient, free energy reactions are never 100% efficient either. The energy always gets lost in some way, shape, or form. Okay. Energy can only be obtained, so in other words, energy can only be left over or absorbed or created, so on and so forth, if the reaction occurs spontaneously. Okay, so let's look at this reaction. Carbon dioxide. And the notes right here don't follow this section. The notes don't fit real well. I should have fixed it, but I didn't. But anyhow, let's look at this reaction and let's try to determine if you think it's going to be spontaneous or not. So we have carbon dioxide gas, and it is going to yield carbon solid and oxygen gas. Right now we have carbon dioxide in the air. Do we just spontaneously see carbon solid forming out of the air and falling on the floor? No. So do you think this is going to be a spontaneous reaction and under these conditions? No, this is probably not. Carbon dioxide does not break down into carbon and oxygen spontaneously at room temperature. We would have to do something to get that reaction to happen, right? Which is why chemists exist, which is why chemists have jobs, is because chemists have to try to come up with ways to get reaction to happen that otherwise would not occur. Okay, this leads us to something called entropy. And I kind of wrote entropy out to the side on my notes right next to measure of the disorder. I wrote entropy delta S because there's not a line there. I forgot to add a line there. Entropy, which is delta S, is talking about how chaotic a system is. Okay, so the definition of entropy is the measure of the disorder of a system. And I always like to compare this to like your bedroom. Okay, your mom, all throughout the week you're going to practice and speech and debate, and you're going to school and you're babysitting and you're doing all of these things. The last thing on your mind is pick up your room, right? So by the end of the week it starts to get kind of messy, right? But then over the weekend your mom nags you, and then eventually you go clean your room so your mom will quit nagging you, right? And then the process repeats over and over and over and over again, right? The amount of disorder is how much entropy, how much chaos is in your bedroom, okay? Which leads us to the law of disorder. Processes will spontaneously move in the direction of maximum disorder or randomness. Your bedroom will naturally get messier and messier and messier unless you put energy in to pick it up. If you don't ever put any energy into keeping your room nice and tidy, it's just going to get messier and messier and messier and messier, right? Unless you do your laundry and you make your bed and you shut your drawers after you open them, so on and so forth. If you don't ever put any energy into the system, it's just going to become more and more and more disordered. Okay, so let's talk about some phase changes. So remember, we just talked about liquid water versus ice water and what happens, okay? So that's like the best analogy I could come up with to try to explain disorder is let's talk about phase changes. And you guys could probably honestly fill in these blanks if you just went along with it. But entropy of gases is going to be greater than that of a liquid or solid. Gases move really, really, really quickly and they're constantly colliding with each other, right? Isn't that a lot more disordered than water kind of moving slowly? And then solids don't move at all, right? Okay. Well, therefore, liquid entropy is greater than a solid's entropy. So if we had to put them in order, gas would be bigger than a liquid. Liquids are going to be bigger than a solid, vice versa, right? Okay, so as a solid melts into a liquid and or a gas, what do you think is going to happen to the amount of disorder? It will increase. Okay? If you take a solid and you melt it into a liquid, or maybe it even then goes into a gas form, your entropy is increasing because your amount of disorder is increasing. It's moving faster. It's colliding more often. Entropy also increases when a solid is divided up, or not a solid, when a substance is divided up into parts. So if I take a giant piece of bread and I cut it up into 1,000 pieces, isn't it a lot more disordered than when it was in one big loaf? So if you take one thing and you break it up into lots of tiny parts, that's a lot harder to keep track of, it's a lot harder to pick up, so on and so forth. So the disorder is also going to increase. So therefore, if you take all of this in together and we try to talk about it in a chemical reaction type thing, entropy will always increase when the total number of product molecules is bigger than the total number of reactant molecules. So if we get more molecules after the reaction than when we started with, our disorder is going to be increasing because we have more things to keep track of. We have more things to do calculations with. The more molecules in the end, the more disorder, the more entropy is going to increase. So let's see if we can fill in the last blank without me putting it up on the screen. If our temperature increases, what do you think is going to happen? Your entropy is going to also increase. So what happens as your temperature decreases? So these are what kind of proportional? Directly proportional. As one increases, the other increases. As one decreases, the other decreases. They are directly proportional. Okay, so if you flip the page, I gave you some graphs. All right, so let's see here. Again, this is my first time explaining this, so hopefully I do a good job. But let's look at the first one. So as we see our heat. Let's treat this middle line right smack dab here down the middle. We have a line right smack dab down here through the middle, right? You guys see that blue line I just added? Let's treat that as like 0. Okay, so if this is like a line graph, let's treat that as 0. Okay, so if we see here, let's look at the first graph. The first graph says that our heat is being released. So what kind of reaction is this? This is going to be an exothermic reaction because our heat is being released. Well, not only is heat being released, but our entropy is increasing, right? So if your heat is being released into the atmosphere, which is honestly going to increase the amount of disorder, right? Releasing heat is increasing the amount of disorder. So that should make sense that your entropy is also going to be increasing, right? If both your heat and our entropy, if both of these things increase, it leads us to a spontaneous reaction. So if heat is being released and our entropy is increasing, then it is going to be spontaneous. It's going to happen all on its own. However, heat and entropy do not always go hand in hand. So if we look at the next graph, if you notice, entropy is increasing this time around, right? Entropy is increasing. But this is not an exothermic reaction because heat is being absorbed. This is an endothermic reaction. But if we look, isn't the amount of disorder, look at how big the arrow is for disorder compared to how big the arrow is for heat. Isn't the disorder arrow bigger than the heat arrow? Yes. So if we look at the overall arrow, is it still to the right of 0? Yes. So even though, yes, it's endothermic, which endothermic usually means that your heat is probably decreasing, or temperature is decreasing, right? Even though that's decreasing, it's smaller than the amount of disorder, so this is still going to be a spontaneous reaction. Okay, so you have to kind of compare how big is the change of the two things. It's not necessarily always one thing or another. You have to compare the size. So this one is also going to be a spontaneous reaction. And then let's look at the last one. This time it's heat being released. So this again is an exothermic reaction, right? Because heat is being released into the atmosphere. But our entropy is decreasing. Okay, but again, let's look at the arrows. Our arrow for the amount of heat being released is bigger than the amount of entropy that is decreasing. So our overall change is still to the right of 0, correct? So therefore, this is also going to be spontaneous, and I can't circle all of spontaneous. Yes, I can. So these are 3 examples of a spontaneous reaction. All right, so now let's look at some examples of non-spontaneous reactions, okay? So, again, we're treating this line right here, pretending it is 0, right? Well, as you notice, we already can see that everything's to the left of 0, correct? So these are probably all going to be non-spontaneous, which you see. But let's talk about each one of them. If we look at the heat being absorbed, that means this is endothermic, right? It's endothermic, but our disorder is increasing, right? So usually when disorder is increasing, it means it's a spontaneous reaction, but not always. Why is this one not a spontaneous reaction? Anyone want to take a guess? the heat being absorbed is way more than the amount of disorder. So because the heat being absorbed is more than the amount of disorder, it leads us to a non-spontaneous reaction. So in other words, because our delta S is smaller than our delta H, it leads us to a non-spontaneous reaction. Okay, so let's look at the next one. The next one, it goes back to being an exothermic reaction because heat is being released into the system. However, our disorder is decreasing. So it's becoming more orderly. It's becoming less products being formed, right? It's becoming maybe a solid from a liquid. It's becoming more and more disordered, more easy to keep track of. So even though it's an exothermic reaction, and exothermic reactions usually are spontaneous because our entropy is bigger than our heat being released because delta S is so much bigger than delta H, it is also going to be a non-spontaneous reaction. So you just really have to get good at kind of comparing and contrasting the two. And then the last one, well, both heat is being absorbed, which is endothermic. Endothermic reactions don't really like to take place all by themselves, correct? Okay, not only that, but our entropy is decreasing, which means it's becoming more orderly. So both of those things do not like to happen on their own, right? So since both of them are decreasing, it makes sense that this one's going to be non-spontaneous, right? So when we're talking about these graphs, if both are increasing, it's probably going to be spontaneous. If both are decreasing, it's probably going to be non-spontaneous. It's when they're moving in opposite directions you have to take into account which is greater. Does that make sense to everybody? Mm-hmm. Okay. Yes.
So if the entropy is greater, then it's going to be non-spontaneous.
It depends on what the numbers are. Like, remember, think of that as 0. If the difference between the two is a positive, it's probably going to be spontaneous. If the difference between the two is a negative number, it's probably going to be non-spontaneous. You have to kind of, and we're going to do some equations in a little bit, maybe today. I haven't decided if I'm going to do the equations today because this is a hard concept. But we are going to learn how to do math with it, and then you'll start to do negative, positives, all that fun stuff. So, turn to the next page. Speaking of positives and negatives, okay, here we have our 3 variables that the unit talks about. We have enthalpy, which is delta H. We have entropy, which is delta S. And we have delta G, which is, what does anyone remember what that is? Free energy. And it's actually Gibbs free energy. That's where the G comes in. Gibbs is the person who came up with the idea of this delta G. So, when you're doing calculations, and we've already talked about enthalpy a lot, we're already honestly pretty good at positive, negative. We already know the first one. When we're doing calculations with enthalpy and we get a positive number, it's telling you that it's an endothermic reaction, which means it's absorbing energy, right? Taking energy into the system. We already know that when we get a negative number when we're doing calculations for enthalpy, it means that it's exothermic, which means energy is being released. We've already talked about this first row, correct? Okay, so, but today we talked about entropy and free energy. So now, leading into kind of what Casey was talking about, if entropy is positive in a calculation, it means that it is more disordered, which means it's Friday and you guys have gone through the whole week and your bedroom is ridiculous and your mom's getting mad. Okay, so if it's a positive number, the amount of disorder has increased. If the number is negative, it means that it is more ordered, or in other words, Saturday, your mom won't let you go to the movies until you clean your room. So then your entropy is going down, right? Okay, the hardest part about this concept is, if you notice, aren't entropy and it's almost like they're backwards, the positive and negatives. So when we do entropy, positive, more disordered. However, in free energy, positive, it means it's not spontaneous. And to me, that was always backwards in my head. It was really hard for me to remember positive and the negative right there. Okay, but if it is a negative number when we're doing free energy, and again, there are some equations that we're going to do with this, and you're going to get results. When it's negative, it means it's spontaneous, which means it'll happen all on its own. So Gibbs free energy and enthalpy kind of go together a little bit to me, but entropy to me is the opposite. That makes sense? I told you today was rough. Okay, so there is a giant table, and we are going to figure it out. So we just did the graphs on this, right? We just talked about these graphs, right? Okay, so Casey asked me, well, if it's positive or negative, or how do I know if it's going to be exothermic or endothermic, or if it's going to be spontaneous or not, so on and so forth. So, and try to do this one row with me at a time so that you're listening to each of my explanations, okay? So, if our change in heat is exothermic and our entropy is more disordered, so if our value for enthalpy is negative, which means exothermic, right? If our value for entropy is positive, which means we're increasing our disorder, if our heat is being released and our disorder, isn't that the graph that we said both are going up? So it's going to yield a spontaneous reaction. This is the easy one to remember, right? Okay, this is an easy one. Okay, and let's actually skip down to the very bottom. Let's do the bottom one now. The bottom one says heat change is positive, so that means that this is also endothermic, correct? But our entropy is negative. And negative entropy means what? Anyone remember? Less disorder. So if we're absorbing heat and we're becoming more orderly, that's not spontaneous. That's the obvious non-spontaneous one, right? So the first one and the last one are what I like to call the give-me's. Those are the ones that are not going to be hard for you. It's all these in between that are ands, ifs, or buts, correct? Okay, so first one, the last one, not too bad. So now let's start in on the second one. The second one is talking about an endothermic reaction. So we are absorbing energy, right? And not only that, but our entropy is positive, which means we have more disorder, right? So if we're absorbing heat, but we're increasing disorder, how do you think we could have a spontaneous reaction? Which one has to be bigger? If the entropy is bigger than the amount of energy we are absorbing, then it is going to be spontaneous, right? Does that make sense? Are we kind of starting to see a pattern here? Because if we look at the third one, isn't the third one the same conditions? It's positive, which means it is also endothermic. The entropy is positive, which means it also has more disorder, right? So if they're both positive, which means it's absorbing energy, but it's increasing in disorder, this time, however, it is non-spontaneous. So which one has to be bigger? The amount of heat absorbed has to be bigger than the amount of disorder gained, right? And then if the heat absorbed is bigger than the amount of disorder, then we're going to have a non-spontaneous reaction. All right, so now let's look at two negatives, the two negative cases. Okay, so negative heat change means it's what kind of reaction? Exothermic. So if we have an exothermic reaction, which means it's releasing energy, however, even though it's releasing energy, the reaction is becoming more ordered. It's becoming, maybe it's going from liquid to solid. Okay, it's becoming more ordered. In which way, which has to be bigger in order for it to be spontaneous? The heat chain has to be bigger than the entropy in order for it to be spontaneous. Because remember, negative entropy is a non-spontaneous thing, right? We don't want to move towards more ordered. That doesn't happen. So in order for this reaction to happen spontaneously, our spontaneous exothermic needs to be bigger than our non-spontaneous more ordered. And then last but not least, we have our negative again. So again, this is an exothermic reaction, and it is becoming less disordered. So the same thing, except this time we're getting a non-spontaneous reaction. So what has to be bigger in order to yield less product? An exothermic energy or less disorder? Which one has to be bigger? less disorder. So the hardest part about this is all of the vocabulary, right? Remembering what entropy is, remembering what disorder is, remembering what enthalpy is, remember exothermic and endothermic, and then we're going to throw in the whole example of Gibbs free energy. The hard part is the vocabulary, not necessarily what it is. We have to figure out some patterns, correct?
So when we drop something like some kind of chemical or compound into another thing that forms the precipitate solid, does that mean that it's obvious it's spontaneous, right? So then it's losing entropy, but it's gaining, but it's also losing heat.
I would assume if you're dropping something in and it's going from, let's say, liquid to solid. Let's say we're mixing two liquids together, and in the process we're getting the solid forming at the bottom. Its entropy is going to be decreasing because it's becoming more ordered, right? But I would assume that our enthalpy is going to be increasing. So I bet you if you touched it, like the glassware, it would be exothermic reaction. Because the only way that would happen spontaneously is if we had this right here. The only way that would happen spontaneously is if our enthalpy change was greater than the loss of disorder. Does that make sense, everybody? That was a really good question. Glad I got that.
It just helped me figure out exactly, because I can imagine dropping something into a solid.
All right, so let's do an example. And we actually already talked about this one. And I don't know why the arrows aren't working. I should probably go back and fix them. But whenever you see that weird W thing, it's supposed to be an arrow.
I was worried.
Okay, so our example, we have H2O solid yielding H2O liquid. Is this going to happen spontaneously under the conditions in this room right now? No. So, when is this process spontaneous? When would this reaction be spontaneous? When would solid naturally, this would be a spontaneous. When would this reaction happen spontaneous? Under what temperatures? When our temperature is greater than 0 degrees Celsius, right? Or you guys know it as 32 degrees Fahrenheit, right? In order to get ice to melt, our temperature has to be bigger than that, correct? I just talked about that. I don't know why I messed up. I don't know. Sometimes when you make a PowerPoint on a PC and then open it on a Mac, it doesn't always work very well. Okay, so when is this reaction process non-spontaneous? When our temperature is smaller than 0 degrees Celsius or 32 degrees Fahrenheit, right? When it is below freezing, we are not going to melt, right? Which is why in the wintertime you have to de-ice your car in the mornings. Right? Okay, so basically, when we're trying to determine spontaneity, a giant factor is what? Temperature. Not always, because sometimes pressure can affect spontaneity. But for the most part, we don't change the pressure, do we? It's hard for us to control the amount of pressure. So for the most part, when we're talking about spontaneity, we're talking about temperature, right? All right, and that ends that funness.